Okay, hello everyone. So this week we are going to study this paper, Flexible High-Resolution Object Detection on Edge Devices with Tunable Latency, published in MobiCom 2021 by Shijiang, Shixilin, Yuancheng Li, Yuanchao Shu, and Yunxing Liu in Microsoft Research, University of Science and Technology of China, Institute for AI Industry Research, and Tsinghua University. So the background of this paper is as follows. We have video streams over the network, and we run object detectors on GPUs in remote clusters, and also then we have the result from those object detectors, which are the frames decorated with bound process. So nowadays, those surveillance cameras are becoming cheaper and cheaper, and we can see that there are more and more available surveillance cameras deployed in our environment. So, and in addition, in the clusters, we can have many different choices of GPUs, including those GPUs with very high compute power and as well as those GPUs with low compute, medium compute powers, such as just nano. And more importantly, the resolution is getting higher and higher, such as the 4K. But there's some problems in existing approaches, right? So in YOLO v3 and YOLO v4, I know the state of art is the YOLO v7. So the direct input resolution for these models are not designed as high as 4K. Specifically in YOLO v3, the input resolution is 416 by 416. In addition, those GPUs are trained on the GPUs. I think those GPUs can be used for gaming, such as RTX 1080, 2080 Ti, and 27. And actually, I purchased RTX 2080 Super myself, although it's a gaming desktop that I use for tuning my models. So and clearly there are some latency patches in clusters, and also in the edge devices with GPUs. So now the things that we send those videos with very high resolution, 4K, for instance, which is in 3840 by 2160. So what's the problem? So object detectors are not well positioned for high resolution images inference on resource constrained edge devices. And the most important challenges is to balance these three metrics. So the first one is accuracy, right? So if we want to have a high accurate, you want to get a higher and higher accurate model, then a typical way would be to increase network size. However, that will, if we increase the network size, we actually introduce more parameters, and there are more floating points in the multiplication when doing matrix multiplication, and that will essentially increase the latency. So we get high latency. And simultaneously, in the edge devices, we actually have limited resources. Although GPUs are very good at parallel computing, and although they have the inference time would be fast, relatively fast compared to CPU. However, it's still a very scarce resource. It's pretty limited. So we want a model to be fast. And to do that, a typical way would be to design a smaller network. So we want to reduce the network size. We can do that we can do it by pruning, for instance. And similarly, lastly, if we want to have a high resolution, if we want to run the network that is able to inference on a high resolution image, we need a larger network size. But that will also increase the latency. So one of the central questions the paper is trying to answer is how to quantify this trade-off. And you might think that well, if we have a high resolution image, a most straightforward and nice solution would be to just downsample the image, right? Yes, I think probably that would be one of the solutions in your head. Well, if we do that, that will curb some accuracy. I will present more about this in greater details, and for now, just summarize in this point. If we just now leave the downsampling, we'll hurt accuracy. Another way would be, well, we can how about scaling up the model? Yes, well, again, that will increase latency. So common approaches, including downsampling, input image recessing, partition, and scaling up and neural networks for short of adapting to video content changes and various latency requirements. So now this paper actually has very detailed analysis quantifying the relation between the downsampled input and accuracy, and also quantify and also analyze how scaling up can increase the inference latency. So let's see them. Well, so before that, there are many. So object detection is a pretty hot topic in recent years. There are many great networks. So what the authors does first is to check 17 object detection neural networks, and they choose 5 typical backbones, including efficient depth and RetinaNet, faster SE neural and SSD mobile net. So and later they choose efficient depth as the main network for analyze to answer these questions. Why? So let's look at this table. So here we have 5 backbones, and here we have a variant. So in short, in efficient depth, it's actually not just one network, it's actually a family of networks that. So in the original paper, they studied how we can scale the network in a compound way to achieve better trade-off between model size and accuracy. For short, and readers can please go to this paper for details. And for the rest, for backbones, they have less variance although you can change those parameters manually, but the state of object detection, at least in 2021, was still efficient at considering trade-off between accuracy and inference time. So this efficient actually includes like D0 to D7, where D0 is the smallest one. The input size is 512 by 512. For D7, the input size is 1500 squared. And if we look at other models, you see that such as the input size, I think a better name would be input resolution. But anyway, it's not a big deal. So these are 640, 1024, 3020, and so forth. If we look at the number of 4K, the input size is actually much smaller compared to 4K. So 4K is like 3800 by 2100. If we go back here, there's huge difference. And a side note is that if we downsample, we lose those high frequency features signals, and those signals would be those high frequency signals. On the other words, it's like it would be less details. So we have less details, and those fine-grained features could be useful for detecting some objects. So they use this one, a speckle, and because they have and they have a wide range of input size for analysis. Okay, and then they use this Panda for as benchmark, which include many videos and many millions of valuable sets of persons and vehicles. So originally the resolution was actually much larger than 4K, the downsample to 4K. They use 80% of the image and use the rest 20% for testing mean average precision. The MAP is a common metrics for measuring a object detector's performance. So let's look at this one. If we so we know that when we downsample image, we'll hurt accuracy. But let's dive into details here. So now in the right picture, we see that. So in the 4K images in the Panda dataset, so nearly 80% of the objects are larger than 582 pixels. So if we downsample them into 320 by 320, so which is the input size of SSD mobile net, then half of the objects will be smaller than 2.82 pixels. So imagine those objects are represented in 2.2 pixels. It's too small for a general existing neural networks to detect. So here we represent the inference latency in the x-axis and the MAP. MAP for now, you could just see that the higher the better. It's one way to measure the to measure an object detector's performance. So they test retina, they test those 5 backbones here, and we see that actually in just nano. So we see that, let's see, efficient nets. So we want we wanted to run faster, so in the x-axis we want those models to go towards left, and we want mean accuracy to be higher. So we want those models to be to go to upwards. So models towards this corner, top left corner, are better, and because that's means a good trade-off between latency and accuracy. So we see that for efficient depth, let's look at this one. So 10,000 millisecond is actually 1 minute, 1 second. So in D6 is actually is around 13 MFP 30%, 0.3, and you take more than 1 second. Okay. So we downsample that is actually, if you compare these numbers into the numbers in the original, in the paper of those models, actually pretty low here. Because when we downsample image, it has lower accuracy. And then later, let's look at this one. What about, maybe we can scale up, right? And when we scale up, how it can increase latency. So let's look at them. So the input size of efficient depth D7 is only 15,000 by 1500 by 1500. Latency is actually higher than 2 seconds based on this this figure, and it would be, so for 4K is higher than this resolution. So it would be impractical to scale up efficient depth to process 4K, which means that it would be more than 2 seconds to process one image. So another way would be that can we do uniform partitioning? So if we do, so what is uniform partitioning? So it's like for 4K image. If we have 4K image, we partition those image into different blocks, and for each block we feed each block into outer detector, so for inference. So if we do this, we may further increase the accuracy, but this could have higher latency. So so here is the picture showing this. Efficient depth noted in blue are the models run on without uniform partitioning. If we do uniform partitioning, we see that yes, we can see the increase of accuracy in the y-axis, but simultaneously the latencies increases dramatically up to, for D7 is actually more than like 10 seconds on just now. So so we have seen 3 very straightforward way to adopt object detectors in existing context. However, so what are the challenges here? So this current image partitioning approach, it doesn't leverage the spatial distribution of objects, it doesn't explore the selection of diverse neural networks. So existing uniform partitioning treats every pixel equally by spending the same amount of computing power on each pixel, so which prevents from achieving a better accuracy latency trade-off. So what does that mean? Well, it means that, so basically it means that for spatial distribution of objects means that objects are usually not uniformly distributed over an image. So it's like in some part of the image, so let's say here we are only interested in persons. We're not interested in carving out, just for illustration purposes. And so in this spatial distribution, these persons let's see, here in this block in blue we see many people in high density. So we can actually use this actually requires a much more better architecture. So we can use more expensive, like we can use a much expensive network to run inference here. And for the block in red, there's no object out of our interest. Note that I know there's some cars, but let's say our interest is just persons. So if there's no persons in these red blocks, we can actually just use very cheap network or just skip them, right? We don't need to actually run very expensive network. Well, and so in these these red blocks, which contains some people, but not that dense, but not in that density, much high density. So it's like some people walking inside the screen, and in that case, we can run neural networks in between. So this is what they meant by spatial distribution. So in short, we can assign different networks based on these distribution. So it's non-trivial to design an ideal partitioning plan to best balance the trade-off between accuracy and latency. So considering multiple factors, including partition size, object density and size, and neural network characteristics. And also we need to consider short-term content dynamics over long-term object distribution to avoid missing objects caused by economic partition. Also, the system must be efficient and lightweight to run on resource-limited edge devices and can be flexible to support diverse latency budgets. So here's the proposal named as remix. So it takes an image as latency. It takes in latency budget and then come up with an image partition and model execution plan, which runs out the shell network, new networks on non-uniformly partitioned image blocks. So let's look at this diagram in greater details. This one includes two main components, including adaptive partition and selective execution. So here, let's look at this adaptive partitioning, how to effectively partition the input image. So this we can compare to this approach to uniform partition. The next one is selective execution. The main intuition is that when there's no objects, well, we actually like skip frames without actually executing some new networks on top of those blocks with no objects. So let's look at this one. The inputs includes candidates of new networks. So you can see a set of new nodes in historical frames and latency budgets. The things that search space of image partitioning and network selection is pretty huge, and it's non-trivial to design an optimal partition plan that best balances the trade-off between accuracy and latency. And also executing partitions effectively requires the awareness of the variance of video content, the new network's capabilities, as well as resource availability, which is unknown and difficult to predict. So before that, since we care about spatial distribution of objects, let's look at the authors actually put different object size and divide them into 3 categories, including small, medium, and large. So small one includes the numbers here is actually in pixel. So in this part is the accuracy of new networks, how they vary among objects of different sizes. So overall, in the x-axis, if we see the increase of the sizes, so all these efficient new networks can obtain higher detection accuracy as object size increases. However, the differences diminishes with the increase of the size. So the differences is actually higher at the beginning, like 3.3, and then in the middle 1.6. In the end, it's only like 10% difference. So more importantly, marginal accuracy gain from different new networks varies significantly across object size. So when we have these new networks, specifically D0 to D7, then we can do some new network profile. So why? So we run the appropriate new network on each block from new network profiler that. So this one we can use it to estimate a new network's accuracy based on object sizes without actually running those, without actually executing those models. So tau is the detection accuracy that at a particular object size level, and IPN can be obtained by using existing public data set rather than the real data captured by the targeted device. Please use Microsoft Google dataset. This one, I think we can get them from the paper directly. And then we have a vector of this one representing a neural network in each object sizes detection accuracy. Or we can just run it. We can test them on the target device. For instance, if we want to run them on just a nano, we can run those models on top of those objects with different object size. It's a one-time effort. So once we're run it, we'll get this vector representing the accuracies of in neural networks on different object sizes. So what they is actually run those execute those networks on the target device multiple times using different batch device sizes. So for each network, they obtain the average latency, L and B, where B is the batch size. And then we need to, so at the beginning, we need to know how to detect distribution. So they run the appropriate neural networks on each block from neural network profiler that estimates neural networks accuracy based on other sizes. Then for one category of objects, their visible sizes is actually similar over time when they are on close positions of the capture view. Some common objects such as pedestrians and vehicles tend to appear in certain regions of the capture views. So we leverage historical frames to learn the distribution of object sizes captured view V from the targeted camera. So we have F, and then have, so the psi is the distribution property of objects on each size level. Then we use an Oracle model to do labeling, denoting as F this level. And then we have the performance estimation, denoted as EAP-TV. So basically, what this one tells us is that so we have, let's go back here first. Lambda P is the object density of P of a block relatively to the whole view V, and N is a one neural network. So we can have these neural networks average position and as estimated average position multiplied by the density, and then we sum all those blocks. So P is block, sum all those blocks. And then let's go back here. And also so each, let's go to dive into this notation. This one is actually one neural networks AP modified by, let's see, go to the object size to get estimate performance. And then in kappa is actually a set of networks used in kappa. So here ELT is the inference latency. They actually sum all of them in for each over all the neural networks over the set of neural networks. Batch B is a batch size. So why I'm doing this? Because we want to quickly estimate the performance without actually executing the partition networks. So now we got latency budget, neural networks profile, and also the estimation of neural networks. Then we can do partition. So so the goal of partition is to run the appropriate neural network on each block from neural networks profile that estimate a neural network's accuracy based on object sizes. And here's the details of this algorithm. it looks complicated. I divided into actually two parts. So the first one is the input and output. The input is essentially denoted in this figure, and we actually have already talked about them. And the output is actually like the obtained function plan. So like go to here is actually the initialization, and so these actually we have already introduced these notations in previous slides, and this one is actually doing the condition here. So they actually use program search. So if if multiple plans in SKP have the close estimation latency within 1 millisecond, then only the one with highest EAP is kept. 10, 19, and 21. And then they set a cutoff latency threshold. Any condition plan would be dropped if its latency is higher than this threshold. Empirically, they set the threshold to 10 seconds. And efficient that D0 to D6 to process 1 4K video. The search space is decreased from 4.3 by multiplied by 10 to the power of 38 to around 9,000 different partition plans with different latency accuracy trade-offs. And these are the examples in my remix on Pendant 4K dataset. And also they analyzed the relation between height and position, so of the central position in Y and the of this height of the centroid position in Y and of the width. So what this one means is that we can actually regress we can predict an object's height and width just based on the pixel location. So now let's talk about partition selection. So they use additive increase multiplicative decrease, so AIMD for short, and TCP congestion control algorithm. And for each divided block P, they assign a penalty window WP that represents skipped inferences. So if they cannot detect any object in P, they linearly increase WP according to WP equals LP minus 1, where LP is the consecutive inference times when no object is detected in P. So once objects can be detected in P instead of multiplicative decrease WT, they conservatively reset WTP to 0 as well as L. So if the block P is skipped, they would decrease WP by 1 for every skipped inference time until 0. And the plan control here is that we want to design set point of the controller is to set the latency budget, and then the measured process variable PV is L is the feedback, and then using SP and PV controller would output the control value U. And this is actually they use a standard PID controller to do this control. So the error value E as the differences between SP and PV, and applies the correction based on proportional, integral, and derivative terms is UT. So each term is associated with coefficient KP, KI, and KD. And this one is a pretty standard PID controller. They evaluate them in the hardware of Jetson AGX, Xaver, Snapdragon, and Current. They use the Salter efficient Dutch and transparent as baseline, as well as efficient Dutch with uniform partition from D0 to D6, and try 7 latency budgets. The selected latency budgets are ranged from 400 milliseconds to 3,000 milliseconds, which is 30 seconds, and donated and to know them. As so TD4 to TD6 and T up 0 to T up 3. So first, let's look at all this one, all 3 hardwares. In the x-axis, we see the inference latency in millisecond. So and the y-axis is the mean average precision. So efficient that actually is denoted in blue, which lies here. If we do uniform partitioning, the accuracy increase, but simultaneously we see a larger inference latency. So remix is noted on the top left corner. So in short, remix is near the top left corner, which is better in terms of the accuracy and inference time trade-off. Here's efficient that the baseline is another baseline uniform partitioning based on efficient depth. And here's the proposed method, remix. And we try to analyze different scenes. So what this one tells us is that they have different distributions. Well, because in different scenes, the spatial distribution of objects are different. So here in A, let's see, in scene B. So scene B, you see here. Let's look at the one in scene, let's see, scene E. So here we see pretty skewed, noted in green because those objects, the distribution is pretty skewed. Here we see high density peoples in these blocks, and here we see almost no persons in these blocks. So that's why we observe those MAP differently. And also we have the performance of plans generated from the ground truth and Oracle model. So recall that we have at the beginning when we don't have any ground truth, it's a common approach to using using an Oracle model, which is a pretty good model to produce those pseudo labels as ground truth. And what this one tells us is that the plans generated from ground truth and the plans generated from Oracle are pretty similar in terms of latency budget and MAP. For the second one, so recall at the beginning we have some historical frames. for the to generate the execute plans. So we see that if we have just one frame, 3 frame, or 5 frame, the performance is pretty similar, which means that we can actually just use one frame to as the history frames, and that will be enough. Then we can decide the different partition plan. And there's some bias between the estimated latency on different latency budgets. So know that so as measure MAP. The question here is that measure MAP is the one we actually execute some models on edge devices to get those numbers. However, that will cost a lot. For estimate MAP, we can we don't actually we use our one-time effort measured MAP accuracy, and then we use them to estimate MAPs of models. So the question is, without executing the models. So the question is, how reliable is these how reliable are those estimated MAP, because we're actually not running those models. And this one shows the correlation for different plans. It shows pretty it shows that those two correlate with each other. And here we have some other micro benchmark as well in terms of latency budgets and in inference latency. And if we try all execution or selected execution, we can see selected execution can achieve lower execution latency. So let's talk about pattern. So pattern basically means that, let's go to the picture here. At the beginning, so recap, if we naively do partition, there will be some objects in the borders that, so those objects will be broken, will be split into 2 parts, and it might not be good for a model to detect if some objects are here, and if they happen to be here and not detected by any objects, then we don't want that to happen. So basically, we, instead of naively punishing the whole image, we actually put more spaces between 2 blocks here, so that we can cover those edge cases. And we can see that the latency. So with pattern, the latency just increased a little bit, but it leads to up to 11.3% relative MAP improvement, and more 1.2% absolute MAP on average. And here we see the energy consumption trace when processing A frames with JSON. Okay, now so we have talked about this paper. So they propose remix, and it's a flexible high resolution object detection framework. And I actually encourage to read the papers in greater details. because they do very comprehensive analysis of those relationships and to decide these plans. Okay, thank you.